So as I imagine you know by now, analysis is the study of a system that has either been designed by someone else or is naturally occurring. You try to look at it and understand what it's doing and understand how it's doing what it's doing. It's really just looking at something that has already been built. Design, on the other hand, is when you do something from scratch. You make something new that later on other people are going to need to analyze. And so when we talk about digital logic analysis, which is the primary focus of today's lesson, we're talking about looking at a digital logic circuit that has already been constructed and figuring out exactly what it does. Now there are two steps to this. One of them is the introductory step, and that is where you're looking just at things having zeros and ones, for example. And so I'm looking just at the inputs to be fixed in binary 0 or in binary 1. And my question is, what is the output? Is it a 0 or is it a 1? And so here you can see the introductory digital logic analysis. All I have to do is take the zeros and the 1s and forward them onto the gates, and then consider what will be the output of the gate. So here you can see I have a 0 or with a 1, and so therefore the output is going to be a 1. I've tried to show in red here what would be done as part of the analysis, whereas the things that are in black would be the circuit that was given to you. Now that 1, of course, is going to follow this wire on over here to the input of the NAND gate. The 1 that was the third input is also going to come over here to the second input of the NAND gate. 1 NANDed with 1. Well, if it were ANDed with 1, it would be a 1, but it's inverted, so that becomes a 0. So you can see here that the output of this function would be a 0. Now that's a fairly straightforward example. Here's a somewhat more complex one, but nonetheless, the same skills really remain. That is to be able to figure out what is the output of a gate given the inputs in zeros and ones, and be able to trace the signals between the gates. So here you can see a 0 at the input. Well, that's going to be inverted to a 1. That will come up here to this AND gate. What's the other input of the AND gate? Well, that just comes directly from the second input. So there's a 1 there, and so that's going to become a 1 at the input. That 1 also goes to this inverter, becomes a 0, and that 0 comes up here to the input of the AND gate. The second input to the AND gate, well, that's just the first input. And so there's a 0 ANDed with 0, that gives a 0. That 0 comes up here, this 1 comes over here, 1 or 0, that's going to yield a 1. And so whether we're talking about a simple circuit or whether we're talking about a more complex circuit, the skills are the same. And really the size of the circuit doesn't have a great impact on the complexity of the problem. You're still looking at tracing signals through and figuring out what is the output of a particular gate, looking just one gate at a time, and the entire circuit will be filled up with 1s and 0s. So this is the idea of considering digital logic analysis with just the literals. We call them literals, the 0s and the 1s. But the problem is now I've done a reasonable amount of work, not a huge amount of work, but I've done some work. And now what happens if one of these two inputs changes? Well, all that work is out the window because now I need to redo all of that work for a new set of inputs. It would be better if I could do it all sort of once and for all and then make any changes if necessary to an equation. You now have enough information to do the digital logic analysis example. If you'd like to pause the video, you're welcome to do that, or you can do both examples after we finish this video. Because I want to show you, in sort of the same video, I want to show you about symbolic digital logic analysis. And in here, what we're going to do is not trace 1s and 0s, but we're going to have variable names. So you can see here, this is input A and input B. Input A comes here to the input of the AND gate. B gets inverted to become B bar. B bar becomes the other input to the AND gate, and then I AND A with B bar, I get A and not B. And that would be the sort of function that represents the behavior of this digital logic circuit. Here's a slightly more complicated one. I have A ORed with B, so the two inputs are A and B. I OR those together. The third input is C. Those are then NANDed together. So I have A OR B and C, and then with a bar across the entire thing. Because when you NAND, you take a bar across the entire thing. So you can see that this is a little bit more work than doing the literal digital logic analysis, but it gives you a more rich, a more valuable, a more universal result as well. Let's see a somewhat more complicated one. Here you can see that I've got a device in which I'm going to have A inverted to A bar, I'm going to have B inverted to B bar, and now I can trace where do those signals go. B bar goes to here, A comes from up here, A bar goes to here, and B comes from down here. And then when I AND them together, I get A bar and B, I get A and B bar. Those then progress on to the OR gate, and when I OR them together, I get not A and B, or A and not B. Now, this is the same circuit that we saw earlier where we did a literal analysis, But here we're doing a symbolic analysis. And so this symbolic analysis will carry through. Even if the inputs change their values, they'll still have the same variable names. So for example, I could consider that equation, f equals not a and b, or a and not b. If I happen to know that a equals 1 and b equals 0, well, then I can plug those into that function. So a becomes 1 and b becomes 0. 1 bar becomes 0, and 0 bar is going to become 1. 0 and 0 gives a 0. 1 and 1 gives a 1. 0 or 1 gives a 1. So I know that if those two inputs are set to 1 and 0, I know that the output of the circuit will be a 1, but I didn't have to go back and look at the circuit. I was able to do that just using the equation, and that is often easier than looking at the circuit. And there are many other examples of places where this symbolic analysis will be more beneficial to us than the literal analysis. So now you have enough information to solve the first two example problems, one on literal digital logic analysis and the other on symbolic digital logic analysis, and then come back and we'll look at a little bit more information.